All right, in this video, we're going to start talking about probability. And we're going to start with the situation where we have some sort of experiment, say flipping a coin 10 times, or flipping a coin once, or drawing a card out of a deck, or rolling 2 dice, whatever your favorite experiment is. And we're going to suppose that capital N is going to be the number of possible outcomes. So if we're drawing 1 card out of a deck, there's 52 ways to do that. If we have 2 dice, there's 36 possibilities. Let's say that we have 2 different colored dice, say one's red, one's black. And capital N is going to be the number of possible outcomes. And the probability of some event happening, if the event, by the way, is denoted by E, then the probability of E is going to be denoted P of E. And so that's going to be the number of ways that the event can happen divided by the total number of possible outcomes. So that's how probability is going to work if we have equally likely outcomes. It's perfectly straightforward. We just have to count 2 things. We have to count the number of ways that the event can happen and the total number of possibilities, the size of the sample space. All right. Again, if we have 2 dice, I like to think of them as different colors. It just helps. It helps us kind of keep track of the different rolls a little bit better. In this case, we have a red and a black die. And so again, there's 36 possible outcomes. So we'll come back and we'll talk about dice here in a second. Let's do an example with dice, actually. Let's say I want to compute the probability that we roll. Let me say this a little bit better here. Let's suppose that we roll 2 dice. And what I want to do is I want to I want to know what is the probability that we roll, and then I'll give you a few scenarios, that we roll, say, a 4, that we roll an even number, or that we roll doubles. Okay, so these are going to be the few scenarios that we're going to look at. And again, remember that since everything's equally likely, so I want to be very careful about what I mean by that. We have 36 possible outcomes. Each of these 36 outcomes is equally likely. I want to count how many ways are there to roll a 4. So what that means is I have to look for the pairs of dice where the number of dots is going to add up to 4. So here we have a 1 and a 3, so that adds up to 4, 2 and a 2, and 3 and a 1. Those all add up to 4. So it turns out that there's 3 ways that that can happen. And so the probability that we're going to roll a 4, so the probability that we roll a 4, there's 3 ways that that can happen. There's 36 possible outcomes in our sample space. There's 36 possible outcomes. And so our probability will be 3 over 36, or 1 over 12, or 8.5% roughly. Okay, so this is 3 over 36, or 1 over 12. And that's it. That's all we have to do. If everything's equally likely, all we have to do is count twice. So next, let's figure out the probability that we're going to roll an even number. And there's a few different ways to do this, but let's just count. Let's just do this perfectly straightforwardly here. So I want to count how many pairs are there where the numbers add up to an even number. So we have 2, 4 like we had before, 6, 3, 4, so there's 5 of those, 8, so we have 2 and a 6, 3 and a 5, 4 and a 4, 5 and 3, 6 and 2, 10, there's 3 of those, and 12. So altogether there's 3, 6, 9, 12, 15, 18 possibilities. So it turns out that the probability that we roll an even number is going to be 18 out of 36, which is 1/2. All right. And finally, let's think about the probability that we roll doubles. What that means is that you have the same roll on both die. So both dice are going to have the same number. And let's see, we can count. I'm going to use purple here. So there's 1, 2, 3, 4, 5, 6 ways for that to happen. So the probability that we're going to roll doubles there's 6 ways for it to happen. There's 36 possible outcomes. So that means that we have a 1 out of 6 chance of rolling doubles. Okay, and so that's kind of our first glance of probability. Now, with probability comes inherent, what's the word? It's not going to be perfectly what we expect, but this is a little glimpse into the law of large numbers. Okay, which the law of large numbers we'll talk about just a little bit, but the idea is that if we were to toss a coin 100 times twice, or even 1,000 times, each time we would very likely have a different number of heads or tails, or a different order that the heads and tails occurred at least. So if we flipped a coin 1,000 times, it'd be very likely that no one experiment would be exactly the same as the other. We would roughly have about half of the time heads and half of the time tails, assuming that it's a fair coin, and so heads and tails are equally likely. But the number of times that you do it isn't going to be the number of times that you do this experiment. You might have a different outcome each time. What is true is that as the number of tosses grows, the probability that your number of, say, heads is going to be 1/2 gets very large. So what I mean is that the probability that you're going to have roughly 1/2 heads is going to be very large. It's going to approach this line. So the more tosses you have, roughly half the time will be heads, half the time will be tails. Even if we don't know exactly the behavior of this blue line here, so even if we don't know exactly how that's going to work, we know that roughly as time goes on, the blue line should get closer and closer to this red line here. Okay, so that's the law of large numbers. If we do something that has an inherent uncertainty, but we can, if we know the probability that it happens, we can predict roughly how many times, how many heads we're going to have. So if I were to take a coin and I were to flip it 1,000,000 times, then half those times, 500,000 of those times would be heads and 500,000 would be tails. Probably not exactly 500,000, but very close. Okay, within a margin of error. And the law of large numbers tells us how do we find that margin of error? How do we think about this? Okay. My screen just jumped here. All right. So a few other basic properties of probabilities. The first is that probabilities of events are always going to be between 0 and 1. If the probability is 0, we say it's an impossible event. If the probability is 1, it's a certain event. Events are, again, just different outcomes that can happen when you're doing some experiment. So the sample space, this is words I've actually already used before, but a sample space is all the possible outcomes in an experiment. An event is just some collection of events that can happen. So if we think back to rolling 2 dice, an event could be, say, rolling an even number, or rolling a 5, 6, or 7, or rolling doubles, or whatever. Okay, so an event just means some subset of your sample space, some set of outcomes. All right, we're not going to get into too much detail here as far as set theory goes, but there's a little bit that we need to talk about. What we're doing here is this box represents the sample space, and the circle represents our event E. So the entire box is the sample space, the circle represents E, and then there's a few different operations that we can do with sets that we'll talk about. There's 3 big ones. The first is what's called the complement of E. So the complement of E is going to be everything that's in the sample space that's not E. So for example, if our experiment is rolling 2 dice and our event is rolling a 4, the complement of E is not rolling a 4. So we denote the complement. Okay, so I should add that this is the complement E-M-E-N-T. That's the complement of E. So it's all the stuff that's not E. So if, again, if we roll, if our event is rolling a 4, the complement of that is not rolling a 4. We denote the complement not E. Frequently, some books like to write E complement, so EC, or E bar. Okay, so there's a few different ways that we can do that. But I'm going to stick with the notation of our book and write not E. We're not going to get too much into probability theory in this semester. This chapter and maybe 1 or 2 following it is really it. The rest of it will be statistics, but at least a little bit while we're doing probability, I want to explain a little bit of set theory too. If we were to have 2 events, A and B, then the intersection of those 2 sets, the intersection of those 2 events rather, is going to be everything that happens in both events at the same time. So if I were talking about the intersection of, say, so let's say that we have 2 sets where A is rolling a 4. Again, we're thinking about dice. And B is rolling doubles. Then let's just take a step back and look at the dice and think about, are there any instances where we can do both of those at the same time? So there's rolling a 4, which we know is one of those 3 events. There's rolling doubles, which is along this diagonal. So it turns out that the intersection is, of course, rolling 2 2s. So 2 2s is going to be our intersection. Okay, so that's the way that both events can happen at the same time. So A and B is rolling a pair of 2s. Okay, so that's how that works. Now A or B, this is called a union. In order to be in the union of 2 sets, it means that you're in at least one or the other or both. So whenever we say or, we always mean the inclusive or. So we allow the possibility that it's in both sets. As long as it's in at least one of them, then it's in the union. So if A is rolling a 4 and B is rolling doubles, so just like before, if A is rolling a 4, rolling a 4, and B is rolling doubles, then A intersect B, I'm sorry, A or B would mean rolling a 4 or doubles. And so there's 8 ways to do that. You can roll a 1 and a 1. I need to go up here for a second. You can roll a 2 and a 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. And then also 1 and 3. It's rolling a 4, and 3 and 1. We've already counted rolling 2 and 2, so we don't need to count that twice. So there's 8 ways that that can happen. Okay, so again, just to recap, not E is the complement. That means that E doesn't happen. A and B means that both A and B happen at the same time. And then in order for A or B to happen, at least one of them has to happen. Possibly both, but at least one of them. All right, 2 events are going to be called mutually exclusive if they have no outcomes in common. So what this looks like is that if you have a set A and a set B, and there's no overlap at all, these are mutually exclusive events. That means if one happens, the other does not. Okay, that's why we say mutually exclusive. I should add that another word that gets used, and I'll try not to use it, it'll be hard for me, but I'll try not to use it, is disjoint. So 2 sets are disjoint if they have no elements in common. Same idea. And there's a much better picture than what I scribbled. I forgot that that was there. Okay. So in the first example, these are mutually exclusive events. They have nothing in common. In the second one, these are not mutually exclusive. They do have some intersection. So there's stuff in the intersection. All right, you can again talk about mutually exclusive for 3 or more sets. And there's a few different possibilities for multiple sets. say none of them have any overlap at all, then they would be mutually exclusive. If there's any overlap at all, so in pictures B or C, then we say that they're not mutually exclusive. That's really the only distinction that we need to make. Okay. And we'll talk about mutually exclusive and rules of probability in just a minute here. So the reason why we're talking about that is that it'll come up in this next section. So P of E, again, this is notation that I've already used, but we'll just use that to denote the probability that E happens. Okay, so it's read the probability of E, or sometimes I just say P of E. And it turns out that if A and B are mutually exclusive, then the probability that A or B happens will be the probability of A plus the probability of B. And in general, that's not going to be true, but if that will be true if A and B are mutually exclusive. That's not true for all sets A and B, but it is true if A and B are mutually exclusive. And it's not hard to understand why this works. If you have two sets, A and B, and you want to figure out what's the size of A or B, it's just the size of A plus the size of B. You don't have to do anything fancy because there's no elements in A and B. We're not overcounting. And analogously, this works if you do this with 3 or more sets. So if A, B, and C and so on are mutually exclusive, then to find the probability of A or B or C, you can just add the probabilities. And again, this does not work in general. This only works when the sets are mutually exclusive. Okay. For example, let's say I want to find the probability that we roll a 5 or doubles. Okay, so I want to find the probability that we roll a 5 or doubles. Here we're rolling 2 dice. I should add, just I'm sticking with our same experiment that we're rolling 2 dice. We have a red die and a black die. So let's say we roll a 5 or doubles. We want to compute the probability of that. Since rolling a 5 can't happen if we roll doubles, they're mutually exclusive. There's no way that we can roll a 5 and roll doubles. So it turns out that we can write that this is the probability that we roll a 5 plus the probability that we roll doubles. And the probability that we roll a 5, we just need to count how many ways are there for that to happen. We could have a 1 and a 4, a 2 and a 3, a 3 and a 2, and a 4 and a 1. So there's 4 different ways for that to happen. The size of our sample space is 36. The probability that we roll doubles is still 6 over 36. Altogether, we get 10 over 36, which if we want to, if we're in a simplifying kind of mood, is 5 over 18. If we're not in a simplifying mood, by the way, I don't care about simplifying ever. 10 over 36 is a perfectly fine way to leave your answer. So that's how this works if 2 events are going to be mutually exclusive. And we'll talk about what happens if they're not mutually exclusive in just a second here. There's the complement rule. So there's a few different ways to think about this, but just the probability that E happens is going to be 1 minus the probability that E doesn't happen. That's the complementation rule. Really, I think the better way to think about this is, what's the probability of E plus the probability of not E? Well, it's going to be 1, because E and not E are mutually exclusive. If E happens, then not E can't happen, because by definition, not E is E not happening. I hope that made sense. But E and not E are mutually exclusive, and every event or every possible outcome is going to be either in E or in not E. So that's going to be some way that you can split up the sample space. So if you add up those probabilities, you should have the total number of outcomes divided by the total number of outcomes, which will always be 1. Okay, so that's the complementation rule. I think that's a slightly better way to think about it. But this rule is totally fine. The probability of E is 1 minus the probability of not E. Not too much more to say there. In general, if you have any 2 sets, A and B, or any 2 events, A and B, and you want to compute the probability of A or B, you have to count much more carefully. I want to just kind of talk through this idea. So here we have A, oops, Here we have A, and here we have B. Let me make sure that I draw this. It's not going to let me undo, but let me make sure I draw this so that it's clear what's going on. And I want to find the probability of A or B. In other words, I want to figure out how many ways can A or B happen. And so I can't just add the probability of A to the probability of B because that's going to be too big of a number. And it turns out what's going to happen is if you think about the intersection, this is A and B. So A and B. I'm counting stuff in that intersection twice. So if there's some outcome that's in the intersection, it's counted twice. And so if I want to count the size of A or B, what I have to do is I have to add the size of A plus the size of B, and then I'm double counting the stuff in this intersection. So we have to subtract off the number of ways that A and B can happen because it's been counted twice. It's been counted once in A and once in B, so we subtract it off so that it's only really counted once. And so then this splits up our set into 3 mutually exclusive pieces. We have A but not B, we have B but not A, and then we have A and B. Okay, so again, I'm not going to get into too much more of the derivation of this rule, but that is how that works. And let's just do an example here. Let's say I roll 2 dice, and I want to compute the probability that I roll a 4 or that I roll doubles. So this is going to be the probability that we roll a 4 plus probability that we roll doubles minus the probability, well, what's the intersection? We've already talked about this. The probability, rolling a 4 and rolling doubles, the way that that can happen at the same time is if we roll a pair of 2s. Okay. So now let's do this. So the probability that we roll a 4, we've already computed, is 3 over 36. The probability that we roll doubles is 6 over 36, minus the probability that we roll a pair of 2s. There's only one way to do that. And so altogether that leaves us 8 over 36, which agrees with the way that we've already counted for this to happen. We counted that there was 8 ways to roll a 4 or doubles. Okay, so this rule seems to agree with what we've already said. I want to add that if A and B are mutually exclusive, so this is just good to keep in the back of our mind. If A and B are mutually exclusive, remember that that means that A and B have nothing in common, and therefore A intersect B has no elements in it. So if A and B are mutually exclusive, and if therefore the intersection has no elements, then the probability of A and B is going to be 0. Because there's no ways for it to happen divided by the size of the sample space. 0 over anything is 0. And so A and B are mutually exclusive implies that the probability of A and B is 0. And therefore, if A and B are mutually exclusive, you don't need it in this formula. In general, you do need that term because not all sets are mutually exclusive, but that's why you get the special case. Okay, so that's the general addition rule.